Thank you for coming to my session. The theme of this session is scaling Rails API to write heavy traffic. First, I will introduce myself. I am Takumasa Ochi, a software engineer and product manager at DNA. I am developing backend systems for mobile game apps. I love developing and playing games. I also love Ruby and Ruby on Rails. This is our company, DNA. Our mission is we delight people beyond their wildest dreams. We offer a wide variety of services: games, sports, live streaming, healthcare, automotive, e-commerce, and so on. We started using multiple databases for e-commerce in the 2000s. Today, game and multiple databases. This is the agenda for today's session. First, I will present an explanation of mobile game API backends and mobile game app characteristics. Also, we will take a quick overview of scalable database configurations. Then, we move on to the API designs for write scalability. There, we will explore application, API response design, and sharding. After that, we will check some pitfalls around multiple databases and test with multiple databases. Then, I will share the consideration of the past, present, and future of multiple databases at our game servers. Finally, we will sum up the session. Okay, let's start with mobile game API backends. Generally speaking, mobile game API backends are split into two categories. One is real-time servers, and the other one is non-real-time servers. In this session, we will focus on non-real-time servers. The objective of these servers are to provide secure data storage and transactions, multiplayer or multi-device communications. For example, non-real-time servers handle inventories, friends, daily bonuses, and other transactions. This figure illustrates an example of API calls. A client wants to consume the energy and help the friend. The server conducts a resource exchange transaction and returns a successful response. This slide explains the system overview of our mobile game API backends. We started developing our game API server in the mid-2010. The system is running on Ruby on Rails 5.2 and mainly running on IaaS. The main API is a monolithic application, and there exist other components as separated services, such as proxy servers, a management tool, and HTML servers for web view. We utilize API mode to minimize controller modules and overhead. Also, we employ scheme-first development by protocol buffers. We use MySQL, Memcached, Redis, and Elasticsearch. Now we will look at mobile game app characteristics. How do you try a new game app? Tap store link, tap the install button, wait a minute and play. It is super easy for players to play. However, it is super easy for servers to write. This slide shows the write-heavy traffic reasons. First, as mentioned earlier, easy install leads to easy write access. Downloading is very easy, and mobile app distribution platforms ensure installs from all around the globe. There is no need to make an account, and first in-game action means first write. Secondly, various in-game actions trigger accesses, especially in write, such as receiving daily bonuses, playing battles, buying items, and etc. Generally speaking, the order of magnitude for mobile apps ranges from 10 kilo requests per second to 1 mega requests per second. Therefore, scaling API to write-heavy traffic is required here. Now we will take a quick overview of scalable database configurations. This slide is an overview of our database configurations. From the application side, we use vertical splitting, horizontal sharding, and read-write splitting. On the other hand, from the infrastructure side, we conduct load balancing on readers and automatic writer failover. Let's look at them one by one. The first technique is vertical splitting. We split the databases into two parts. The first part is common. There is one writer node, and this is optimized for read-heavy traffic. We prioritize consistency over scalability here. For example, game setting data and pointer to shard are stored in the database. The other part is shard, which is the main focus of today's session. There are multiple writer nodes, and this is optimized for write-heavy traffic. We prioritize scalability over consistency here. Also, this shard database is horizontally sharded. For example, player-generated data is stored in the database. This is the horizontal sharding. We take data locality on a player and partition them by player ID, not by resource types. This architecture is effective to hold consistency on each player and efficient for player-based data access. We use a mapping table called player shards to assign a shard. We decide a shard on the player's first access by weighted sampling. This dynamic shard allocation is flexible for adding new shards and balancing the load on them. There is a limitation of a maximum inserts per second for this architecture. For example, thousands or tens of thousands of queries per second are the limitation of MySQL. If we hit the limit, we can use a range mapping table or distributed mapping tables. Of course, we utilize read-write splitting too. In our case, we use manual read-write splitting. This is complex but efficient. API servers access writer nodes to retrieve data, used for transactions and the player's own data. On the other hand, API servers access reader nodes to retrieve data not used for transactions and the other player's data. From the infrastructure side, we employ several multiple database systems. The key concept here is do that outside of Rails. This concept increases flexibility and achieves separation of concerns. In our case, we use a DNS-based service discovery system with a custom DNS resolver on Rails. Load balancing is conducted on the weighted sampling of IP addresses, and automatic writer failover is executed by changing the IP address to a new writer node. So, every aspect of multiple databases is indispensable for scalability. Let's dive deeper into some critical features. Now we are going to explore the API design for write scalability. Let's begin with traffic offload by replication. Replication is an effective technique to offload read traffic. Here, we replicate DDL and DML from writers to readers, and almost the same data is available on reader nodes. By offloading read traffic to readers, we can reduce the writer's load and make the system scalable for read traffic. However, there is an replication delay. Strictly speaking, the latest data is only available on the writer node. Then, how do we balance between the scalability and the consistency? The solution is read-your-write consistency, which ensures consistency on your write. This slide shows the read-your-write consistency in Rails 6. The solution is time-based connection switching. When there is a recent write by the data changer, Rails connects to a writer. This connection switching is the default in Rails 6, and 2 seconds replication delay is tolerated as default. Using this architecture, we gain high scalability for read-heavy applications, and strong consistency is guaranteed where players care. On the other hand, there are mainly 2 cons for this architecture. The first one is that this is not suitable for write-heavy applications. Because of the higher proportion to the writer, traffic offloading is not so effective. Also, we have to take a severe balance between replication delay and the write-read ratio. When the tolerated replication delay increases, the write-read ratio also increases, which means not scalable. So we must further improve this for write-heavy traffic. This slide explains the read-your-write consistency for write-heavy applications. The solution is a resource-based strategy. Players' own data and critical data are fetched from writer, and other data are fetched from readers. One of the pros of this architecture is the effectiveness for write-heavy traffic. Also, much longer replication delay is tolerated, say tens or hundreds of seconds. This magnitude of replication delay is often invoked by cloud infrastructure failures or by request surge. This architecture is effective to offload inter-player API traffic because there are fewer connections to writers. The cons of this architecture are the complicated business logic and the ineffectiveness of offloading intra-player API. In other words, this architecture has greatly enhanced scalability, but further improvement is required considering the intra-player API. Okay, now we will take a look at traffic offload by resource-focused API design. Let's conduct a case study. The scenario is buy hamburgers and add them into a knapsack. There is a knapsack with items, a wallet with money, and infinite hamburgers. Player A buys hamburgers and adds them to the knapsack. The wallet balance will decrease and the items in the knapsack will increase. What APIs are required for this scenario? There are 3 required APIs: create burger purchase, index item in knapsack, and show wallet. You can see the Rails routes on your right-hand side. The routes consist of 3 resources. Let's see the API call sequence on the left-hand side. In the first access, a client calls index item in knapsack and show wallet. Then the player decides what to buy, and the client calls create burger purchase, index items in knapsack, and show wallet balance. Again, the player decides what to buy, and the client calls all the APIs. There are many API calls to access writer. This write-heavy traffic is because of the recent write for read-write in Rails 6 and because of the own resources for read-write for write-heavy traffic. How do we solve this write-heavy API calling? The question is, why do we fetch the data from the writer? This is because the items and wallet are changed. What exactly the changed items and wallet? We can find them in the controller. They are the resources client want to fetch and the resources write request affected as a side effect and the resources Rails has on memory as active record instances. So, the solution is to include all the affected resources in API response. In this scenario, there are two kinds of affected resources. The first one is target resource, which is the primary purpose of the API. In this case, the burger purchase. The other one is affected resource, which is the side effect of the API. In this case, items in knapsack and wallet. On the JSON sample on your right-hand side, you can see all the resources are included in the response. And you can see the API call sequence below the JSON. Here, the client calls index item in knapsack and show wallet on the first access. This sequence is the same as the original API call sequence. However, after deciding what to buy, the client calls only create burger purchase. This is because all the required resources are included in the response of create burger purchase. So there are no read API requests except the first one, and there are no writer database accesses except for the transaction itself. The absence of requests is beneficial both to databases and to clients. Although there are duplicate resources and increased complexity, we have made writer databases focus on transactions, which is the only thing not achievable by readers. This slide explains the summary of the mixed result of replication and resource-focused API design. On the one hand, read-write consistency based on data's owner is effective for write-heavy traffic, interplayer APIs, and sharding. On the other hand, including affected resources in write API response is effective for minimizing read API requests and writer database accesses. Also, it is effective for intra-player API. As a mixed result, we have obtained the following effects. Firstly, we have gained a complex but adaptive architecture due to manual read-write switching. Secondly, we have achieved maximum traffic offload due to affected resources in write API responses. Thirdly, we have achieved robustness over replication delay. The architecture tolerates a very long replication delay. So we have achieved both consistency and write scalability with higher robustness over replication delay. Now we successfully let writer databases focus on transactions. However, what if the number of transactions exceeds the writer database's capacity? The answer is sharding. Now let's see the scalable data locality for sharding. General multi-tenant sharding splits the data by the owner tenant. There is no interaction between shards. This is the scalable architecture. We only have to add another shard to scale. Also, sharding is the valid architecture to guarantee the best data locality in multi-tenant sharding. Yeah. How about a single-tenant multiplayer game? Interaction between shards is the most critical feature required for single-tenant multiplayer game. Players in one large game world must interact with each other. Also, sharding does not guarantee the best data locality by itself. Furthermore, sharding can invoke a consistency issue on node failures or network failures. So we have to handle it. The objective of data locality is to improve performance and consistency by locating data wisely. The basic strategy here is, first, consider cross-shard operation cost as expensive. Second, decrease the access shard and additional computation per request. Then, make a balance on accumulated cost. Let's conduct some case studies on the architecture. The first scenario is train myself and respond to call for help. In this scenario, player A and player B train themselves. Then player C calls one of them for help. Here, there is no need for the latest trained state. The requests consist of 95% everyday training requests and 5% occasional help requests. The solution is a pool architecture. You can see the rails and databases on the figure. We locate the data to the owner shard indexed by player ID. Then, 95% of write requests involve just one writer, and 5% read requests involve one writer and one reader. This architecture is performant on the majority write requests. The next scenario is send gifts, list gifts, and receive gifts. In this scenario, player A and player B send gifts to player C. Player C lists them in chronological order. The requests consist of 30% occasional sending requests and 70% everyday listing or receiving requests. You can see the figures on your right-hand side. The solution here is a push architecture. We locate the data to the receiver's shard, indexed by receiver player ID sent out. By doing this, 30% write requests involve two writers and 70% read-write requests involve just one writer. Although there is an additional cost on sending gifts, this architecture is performant on the majority read-write requests. Also, there is no merge sort cost due to pre-indexed data. The third scenario is become friends and list friends. In this scenario, player A, player B, and player C list friends. Player C become friends or linked with B. The requests consists of 95% everyday listing requests and 5% occasional linking requests. The solution here is double write architecture. We locate the data to both shards indexed by player ID and friend player ID. Then 5% write requests involve maximum 2 writers, and 95% read requests involve only 1 reader. This is performant on majority read requests. Let's look into a more complicated scenario now. The scenario is join a guild and defeat a raid boss. Player A, Player B, and Player C join a guild. They fight together against a powerful enemy. They share a limited amount of consumable weapons. Each player's attack and the enemy's attack change the current situation. Both acid and performance are critical for updating player's health, state, formation, and enemy's health, state, and guild's remaining weapons and state. The solution is partial resharding. From the database's viewpoint, players belong to different shards, and players belong to the same guild. Both acid and performance are required here. First, select another shard for the guild by weighted sampling. You can see the new shard with the sunglasses on the figure on your right-hand side. Then reference the new shard from each player's original shard. At the design phase, we extract critical resources for the raid boss. For example, health, state, formation, weapons, and so on. Then locate the extracted resources on the guild's shard. This achieves acid and performance because the number of involved shards is only 1 for transactions. We can leave the non-critical resources to the original shards. By this way, there is no cross-shard overhead for guild-based transactions and APIs, and acid is also guaranteed. We have successfully improved data locality and achieved scalability. This data locality technique benefits not only conventional databases but also some distributed databases, considering the under-the-hood architecture. However, we have not yet fully solved the difficult issue for conventional databases. Now let's look at consistency for sharding, the last part of API design. Keeping consistency over multiple databases is a difficult problem, especially back in the mid-2010s when our game server was born. Someone says, two-phase commit can ensure atomicity over multiple databases like exit transaction. This is the overview of the two-phase commit for comparative study. First of all, there are two kinds of participants here. One is transaction manager, in this case API server, and the other one is resource manager, in this case MySQL database. The sequence is as follows. First, transaction manager asks resource managers to update records as usual. And transaction manager asks resource managers whether or not they are prepared for commit. Then, resource managers execute the transaction up to the point where they will be asked to commit. After that, resource managers respond to transaction manager whether they can commit or not. If all the resource managers can commit, then transaction manager tells all the resource manager to commit it. However, if none of the resource managers cannot commit, then transaction manager tells all of the resource managers to roll back it. This is simple at least for nominal cases. You can see the more casual description of the sequence in the picture on your right-hand side. Here, transaction manager asks resource managers whether they can commit or not. Transaction manager is asking for an explicit agreement here. However, unfortunately, the MySQL document says prior to MySQL 5.7.7, exit transactions were not compatible with the application at all. Also, two-phase commit like exit transaction has potential issues for scalability. Prioritizing scalability, we have to relax the atomicity while maintaining the practically acceptable consistency. Let's conduct another case study for this consistency. Player A consumed item in knapsack. Player B received the consumed amount as a gift. Pretty easy, isn't it? This code is the result of eventual consistency implemented in Rails 6. Seems difficult because of connected to. But do not worry, we will explore this one by one. Rule 1 is reduce the risk of cross-shard transaction anomalies. Before proposing this rule, we should check the precondition for relaxed cross-shard transactions. First, all resource managers are composed of the same architecture, MySQL, and then resource managers are prone to fail for a continuous period of time. For example, failure in cloud infrastructure can trigger this kind of failure. Also, resource managers are unlikely to fail only on commit. Let's look at the figures on your right-hand side. There are two MySQL databases in the middle. The top part of this figure is a conventional two-phase commit, and the bottom part of this figure is a proposed relaxed transaction. In the latter case, transaction manager asks the resource manager to update the record, and the resource managers respond with OK. Then transaction manager assumes that, yeah, they can probably commit. And transaction manager executes the commit order. Let's take a look at Rails code achieve the relaxed transaction. In the beginning, there are two consecutive nested transaction blocks. These nested transactions execute a consecutive commit at the end of the transaction block. Right after the beginning of the transaction block, you can see the player.block.findPlayer.id. This code is locking granular resources to avoid race conditions during the transactions, which further ensures the success rate of the transaction. The main business logic is omitted in this example. Finally, toward the end of the transaction block, there are consecutive save methods. This code is the critical component in relaxed transaction. The Ruby code invokes consecutive update queries followed by consecutive commit queries, which minimizes the time and uncertainty of a transaction manager and resource managers. The typically expected but very unlikely anomalies are as follows. 1. Transaction manager or Rails failures between consecutive commit. The next one is network failures between consecutive commit. And the third one is sender shard node failure before the last commit. Here, we have achieved an XA competitive success rate for nominal cases, except for the difference from XA prepare to update, and for the difference from XA commit to commit. Also, there are no blocking factors for node or network failures. Although we do not have a persistent log on resource managers, we have gained a reasonable success rate for nominal cases here. Rule 2 is to keep inconsistency observable and acceptable. Before proposing this rule, we have to know that there are 3 states for cross-shard transactions. One is none of the shards commit. This is the failure state. And the second one is some and not all of the shards commit. This is the anomaly state. And the last one is all of the shards commit. This is success state. In order to recover from the anomaly state, the general two-phase commit forces all the failed shards to commit, so we do the same thing. Firstly, we serialize and control the order of commit. This reduces the anomaly state to n-1 for the number of resource managers. Secondly, we make the inconsistency observable from transaction manager. In this scenario, the sender. This is the trigger for retry or recovery. After that, we make inconsistency acceptable from others or from the next action. We let the inconsistency behave as if the transactions are all successful. Also, the next action should not affect recovery or vice versa. This practice leads to a non-blocking characteristics. Now let's see the Rails code on your right-hand side. In the beginning, you can see the outer transaction block is the sender shard. So the anomaly case is that receiver reached commit and the sender reached rollback. Let's imagine what will happen to this anomaly at the bottom of this transaction. First, sender history and the sender summary would not be saved in this case. The absence of history is observable, and the sender can retry based on that. Also, receiver gift would be saved in the anomaly case, and the receiver can use receiver gift regardless of the sender's transaction. By this observable and acceptable inconsistency, we have gained a non-blocking start point for retry or recovery. Then, here comes Rule 3. Keep idempotency and reach eventual consistency. The proposed solution utilizes retry because the retry is the simplest but reliable method. Actually, it works even for the network failures outside the server systems. In order to utilize retry, we have to use an idempotency key to identify the resources. The identifier is often called transaction ID, idempotency key, or request ID. We build the business logic assuming the inconsistency, history-like table, and find or initialize by is a convenient way to handle this inconsistency. Let's look at the actual Rails code. This code is the main business logic of the cross-shard transaction. In the middle, you can see the returnif sender history.persisted. This code ensures the idempotency for retries. If the sender history persisted, it means that all the transactions successfully reached commits. No further update is required. At the bottom, you can see the gift.find or initialize by. In the anomaly case, the gift already exists, so the find or initialize by migrate this inconsistency efficiently. By introducing idempotency and eventual consistency, we not only overcome database anomalies, but also failures outside the server systems. Both eventual consistency and scalability are achieved. I think this is sufficiently practical. Are you not satisfied, or do you require more strict solution? Then, Rule 4 meets the requirement. Rule 4 is utilize at least once message queue for strict completion. The precondition for this rule is that business logic already complies with Rule 1, 2, and 3. We divide the architecture into two parts. The first part is the enqueue phase, and the other one is the dequeue phase. In the enqueue phase, we save data to a single shard database. The ACID is guaranteed here. Then we enqueue the message referencing the data within the transaction. This guarantees at least once message existence. Then make the message dequeued only after the transaction is finished. Force timeout both on Rails and on databases, and use perform later for delayed dequeue. Let's see the Rails code on your right-hand side. In the middle of the code, you can see the wait 30 seconds and perform later within the transaction. Given MySQL and Rails timeout, it is guaranteed that the transaction will reach either commit or rollback when the active job is performed. In the dequeue phase, just retrieve the messages from the queue and check if the data in the database exists. If not exist, then the transaction reach rollback. Do nothing. If it exists, then the transaction reached commit. Continue the process. Then conduct idempotent business logic and be sure to finish the message only after the business logic succeeds. This guarantees at least once job execution. Also, do not forget to consider the risk of review process clash. By this architecture, we have achieved a quasi-theoretically guaranteed completion of cross-shard transactions. Thus, we have acquired practically acceptable consistency without losing scalability. This is essentially a concern of databases, so we should bear in mind this should be more elegantly solved by sophisticated databases. So, is it all the things we have to do for right scalability? There's more. And we are going to look at the pitfalls around multiple databases. The objective of sharding is horizontal right scalability of databases. Specifically speaking, given n as number of shards, keep time and space complexity to O of 1 or at least O of log n. Sounds simple and trivial. We have actually achieved that by sharding. However, there are more pitfalls around us. The one pitfall is the number of connections per database. The connection pool of Rails is to cache and reuse the established database connection for performance. And there is a limitation over this because the cached pool cannot be shared across processes or across instances. Also, the Ruby 2 GVL forces only one native thread is runnable per process. The result of these two limitations lead to the number of processes larger than CPU core. And generally speaking, there are many API servers to the many shards. So let's do the math here. The number of servers is 1000 and CPU core is 32 and the pool connection per process is 5. Then we can yield 160,000 or 480,000 connections per database. Actually, this number exceeds the maximum connection of MySQL and PostgreSQL. And we can see the deteriorated database performance due to many connections, like memory and CPU. Actually, the typical default by cloud computing providers is around hundreds or thousands, so we have to target this value. The strategy of reducing the number is like this. First, assume average O of 1 for actually used database connections per request, and then release the connection to where every thread or process can retrieve. The solution 1 is multiplex connections at proxies between databases and API servers. The PG bouncer for PostgreSQL is famous for this solution. The pros of this solution is there is no connect overhead at databases. However, there are cons. As for the transaction pooling, some database features are disabled, and regarding session pooling, clear connections are also required. And the solution 2 is clear connection pool after each request. The active record refresh connection is famous for this solution. The pros of this solution is there is no additional components required, and full database features are available. Although these have a connect overhead at databases, this is not so problematic for MySQL, and we have achieved low connection number with the solution 2. The next pitfall is the connection reaper thread per API server. The connection reaper thread is a thread to periodically flush idle database connections. This was enabled by default in Rails 5. The original design of reaper thread led to a reaper thread created per database spec. So let's do the math here again. The number of unicorn processes is 100 and the number of shards is 300, and then the number of writers and readers are 2. Then we can yield 60,000 total number of reaper thread here. So this is actually exceeds the default parameter in kernel, and also we can see the deteriorated performance due to many threads. Actually, in the Rails 6, this is already fixed. And if we are using Rails under 6, you can set the reaping frequency equals nil and disable reaper thread. The summary of pitfalls is like this. We have learned that even the elaborately crafted code fails before a huge number of databases, and there might be another pitfall behind you. So, how do we avoid pitfalls? There are too many things to consider. Then it comes the test. Test with multiple databases. If we haven't tried it, assume it's broken. We should test multiple databases. The recommendation for use real multi-databases in test is, first, use real multiple database configurations at test. Avoid stub and use real databases and middlewares, and separate reader and writer connections. And there should be more than one shard for horizontal sharding. And we love factory bot over fixtures because it can test the dynamic shard allocation and access. And we recommend use real transactions on test by setting the config. And we also simulate partial transaction failures. And these practices can detect wrong understanding of middleware behavior, wrong choice of reader-writer connections, misallocation and misaccess to shards, and wrong handling of recovery retry over partially failed transactions. Also, we had injected anomalies in sandbox environment. The purpose of sandbox environment is develop client system and conduct Q&A on integration of client server and other components. The anomalies should be tested there. In our case, we had always 10 seconds application delay, and we implemented debugger to inject exceptions for important and complicated APIs. These practices can detect server bug on accessing readers, and client bug on relying read API for the related data, and many architecture bug on the design of read-write API, and idempotency and eventual consistency. And also, we highly recommend conducting load tests before service launch, because this is the most unpredictable part on multiple databases. For example, does the app work with 10 shards, 100 shards, or 1000 shards? And actually, it is required to provision servers to the maximum load on the production. And these practices can detect uneven distributed load of partitions and time and spatial complexity of O of n or greater, and other issues due to the real scale. Now we can relax ourselves in addition to relaxing multiple databases. Lastly, past, present, and future of multiple databases at our game server. In the past, our project started with 4.2. This is the latest version of that time, and there is no native multiple support then. And so we have extended Rails and various gems, and we make many monkey patches. For example, in-house gem out track was created, and rich pool was extended. And we take priority on performance over complexity, and we take priority on verbal syntax over implicit computation there. We had implemented various features, and this was successful supporting games. Then the current. There are two different Rails versions. Our Rails is 5.2 plus extended gems plus monkey patches, and upstream Rails is 6.2 plus native multiple database support. The feature discrepancy is shrinking. For example, common pitfalls are being fixed at upstream Rails, and useful features are being implemented at upstream Rails. However, there is a growing code discrepancy, because there is different code to achieve the similar things, and there is more sophisticated design at upstream Rails. So which way are we going? Of course, on the Rails. We are considering to upgrade to upstream with simplified multiple databases. I think this is sustainable continuous development toward the future. Also, we are considering to migrate and contribute our technical expertise to Rails. This not only benefits Rails, but also benefits us. And we can turn the technical debt into technical assets. We'll be back on Rails. So, let's sum up today's session. We have explored various techniques to scale Rails API to write heavy traffic. First of all, we utilize all aspects of multiple databases. Vertical splitting, horizontal sharding, replication, and load balancing are all necessary. Then we let writer databases focus on transactions. Replication can offload the read traffic, and resource-focused API response design can minimize unnecessary data access to writer. Next, we optimize data locality to reduce the cross-shard performance overhead. We have explored pull, push, double write, and partial resharding architectures. After that, we introduce practically acceptable and scalable consistency. It consists of risk minimization, observable and acceptable inconsistency, and eventual consistency. We also learned some pitfalls and risks even for the elaborately crafted code. Therefore, we recommend a test with multiple databases. This can ensure all the techniques here are working as intended. By using real databases, real anomalies, and real scale, we can ensure everything is working well. Lastly, I believe it is crucial to contribute to Rails upstream, which turns technical debt into technical assets. Thank you for listening. DNA loves Rails.